Okay, hello. I'm going to be continuing on the theme of whispering gallery modes, this time for dispersion analysis, which not only applies to cavities, of course, but just applies to any waveguide going in any direction for whatever reason. Hey. Oh, hold on. So, as I'm sure you've probably heard of, dispersion is when some frequencies travel at a different speed than other frequencies. And so this has a variety of consequences for broadband optical kind of applications in photonics, in any photonics. So why is this important? Well, I'm sure many of you have a big variety of different projects in optical related things or quantum optical related things, and perhaps some of you might be interested in doing some nonlinear coupling of some sort, and in which case dispersion is absolutely essential to get a hold of, basically. There's some writing in my slides, but you don't have to read it as I'm talking. It doesn't matter. But so basically, if you have coupled optical modes in a cavity, for example, whether their coupling is mediated by these two conditions. Obviously, conservation of energy. So in this example, this is a four-wave mixing example where you have four interacting optical modes. For them to interact, they have to have energy conservation. So in this case, two pump photons convert to two signal and idler photons that match in frequency like so. And they also have to match in the momentum domain. They have to have conservation of momentum, which means their propagation constants must also match in the propagation direction. So in this case, you might have two pump photons converting to two other pump photons, and there might be a phase mismatch between the two. And that phase mismatch, where the phase mismatch is zero, is where you will get mode coupling, basically. You might get a generation of modes like sidebands, or if you insert two or three modes, you'll get a fourth mode generated, or you might get a modulation of the inserted signal mode that you want to modulate. Oh, and also, of course, maybe as you know, if you insert pulses through dispersive domains, they'll broaden in a variety of ways. That's linear optics. That's also good to know if you're working with pulses. But I believe Hiron has already explained some of this. But if you imagine a cavity has a series of resonances at a series of resonance frequencies. And you might naively assume that all the resonances are exactly evenly spaced by the free spectral range. But really they're not, of course, because different frequencies travel at different speeds. There's an adjusting thing, and basically there's a deviation. So here's a frequency comb of uniformly oscillating modes, but well, they're a bit dark. But you can see that the cold cavity modes gradually deviate from them, and this is basically why, for example, if you have a frequency comb set up in a cavity, this dispersion will, in fact, limit the broadband pattern formed inside that cavity. Or it will also limit the frequency shift with which you can couple modes non-linearly. Here's an example of a resonator. Hiron showed this before. This is a crystalline resonator with the mode. And if you took away this uniform frequency grid that you would expect the modes to be on, and then plotted where they actually are against that, you'll find there's this deviation, basically. The farther away you get from the pumped resonance, the more deviated the cavity resonances become, and the less coupled the oscillating modes are. And that's dispersion manifest in cavities. For very broadband systems, you'll get further, more interesting dispersion profiles. Oh, by the way, so this is the frequency of each cavity mode. So that's the offset, and that's the FSR, and then this is the various other terms. And you might find with these sorts of terms, the cavity resonances go off phase matching and then come back into phase matching at some shifted wavelength, and then you'll get strong coupling. You'll get suddenly a resonant radiation forming or a dispersive wave, like in this example. So say you want to do a broadband or coupling experiment with a cavity of some kind, but really you don't know where to start. Really, you might have a material, you might know what the deposition thickness of that on a chip, but you don't know what the shape of the resonator should be. You have no idea maybe what FSR you want. Even if you did know the FSR you want, you don't know if you get the right length, because you're not sure what the group velocity is in this material, in this waveguide. And yeah, you don't know how much space you have on chip. You might have a simple ring resonator, or you might have this tube or this coil or this Nintendo controller. Or so it's good to start with just simply calculating the per meter dispersion of a straight waveguide, and then figuring out, once you decide on your resonator architecture, then go for a full bent waveguide dispersion calculation with Comsol. Hiron before was doing whispering gallery mode eigenfrequency, which is finding the exact frequency of a mode given a mode number. And as he mentioned, that requires some iteration. It's very accurate, and it's actually not necessary for finding the broadband dispersion of a cavity. We can just do 2D mode analysis, for example. So in Comsol, which I'll show you later, you just do 2D geometry mode analysis. So that means you pick a frequency and then you calculate the mode and the propagation index. And yeah, so like the whispering gallery mode thing, you'll come up with a variety of modes. And we're just going to go with a simple square, a rectangle. You might have a trapezium or a fancy shape, but let's go with a rectangle. And also, let's just go with the fundamental modes. And so I think, as you've seen in in at least one previous talk, you can reduce the complexity by knowing that there's symmetry. So if we want the TE mode, we put a perfect magnetic conductor just in this line here, and then we leave the perfect electric conductor here for the TM mode. Which we'll do. As you just saw earlier, we can put in materials that have inbuilt broadband refractive index profiles. So we will do that for SiO2 for our cladding of the waveguide. But as for silicon nitride, there is silicon nitride, but it's not calibrated for our example. We're going to do 1550, and neither of these are correct. But that's a good opportunity to make up our own silicon nitride with our own Selmayr equation. And this is actually really important because the dispersion is really both the material dispersion of the material and the waveguide geometric dispersion both really contribute to the overall dispersion profile. So it's important that you acquire quite an accurate, experimentally accurate equation for your material, whatever that might be. Here it's going to be silicon nitride, and this is going to be the equation. Here it is in copy-paste format for you to just copy-paste if you want to do this from scratch. Hiron already explained meshing, so you probably get the idea. We'll see it later. And you'll see how I set up the model. Okay. Actually, is there a way to quickly duplicate displays? I forgot. Actually. Yeah. Okay. Ah, awesome. Thanks a lot. Great. So we're going to go with 2D. 2D, electromagnetic waves, frequency domain. And mode analysis. No. Okay, so we'll start by right-clicking here and putting in a few parameters, such as, okay, sample frequency. And that's just going to be 192 terahertz. And then we'll have waveguide, waveguide height. That's going to be 0.8 micron. And waveguide width, that's going to be 1.6 micron. Like that. Cool. So we'll go straight to geometry. This is core. Let's see, width, waveguide width, height, waveguide height, divided by 2, because we're actually going to split this in half. And we want it in the middle, so this is in the corner, so this is waveguide, waveguide width. Look at the 2. Okay. And then just another rectangle for, let's see, width of 10. Oh, whoops, hang on, I always forget this. Just in geometry, change to micron. Okay. Or it doesn't matter, you know. Or actually, no, it does matter. So yeah, this is going to be the cladding. Yeah, so something like that. This is just a straight waveguide, so we're going to be calculating the propagation dispersion. Okay, we're going to add a material from the library. You might find this in optical materials, inorganic materials, and down here SI2. SiO2, this Malletson one. This is the really stereotypical kind of optical SiO2. And look here, it brings up a selection, so we could select the cladding. And that's easy. Then we'll add a blank material. Call that SIN. During this, if you ever get lost, just load the straight waveguide model in the Google Drive, and it'll all be already done. Okay, so this SIN, this is the core. Click the core. And here, in refractive index, we'll just put in SIN like that. And that's undefined right now, that's why it's yellow. So back up here in definitions, we'll make a variable, or variable table. And in that variable table, we'll make in SIN. And then I'll just quickly go back to my slide. Copy this, because it's an easy expression. I mean, it's good to copy it. Right. Down here. It's times a million because it has to be in micron. This is an intrinsic variable to the model of the wavelength. Yeah. Okay. So the material's all good. For the science, because like I said earlier about symmetry, let's put in perfect magnetic conductor and just select the bottom like this. Great, that's easy. If we want to actually find the TM modes, because okay, now it's overridden the perfect electric conductor over the side here, but if we want to go back and find the TM modes, we could just disable this, and then it'll go back to having all perfect electrical conductors. So I'll quickly set up the mesh. This will be a reminder on what Hiram did. Let's just do go ahead and just do two free triangulars. One free triangular, you select domain here and select the core. Oh yeah, and then you go in that and have a size parameter. Now, and the thing is, if you do extremely fine, it's not fine enough. It's not fine enough. It's not extremely fine. So you need to go maximum. You need to go custom and maximum element size about 0.05 micron. Really, that's fine for that one. And for the cladding, I guess you go minimum 0.05, maximum 0.5, because it doesn't matter. But also you don't want the triangles to expand too much away from the core, so maybe change this to 1.1. All of this will adequately capture the evanescent field as well as the internal field. It must capture the evanescent field for an accurate propagation constant. Okay, and so here in mode analysis, let's actually put in sample frequency, because this is the parameter we made up before. Right. I hate this. Sample fric. Sample fric, okay. The refractive index of silicon nitride is about 2, so let's just put in 2, and then go smaller. Smaller real part, because it won't be bigger than 2. And for example, we could just look what we will get at one particular frequency to just see what we're looking for. So here's one sort of fancy mode. There's the third harmonic and the second harmonic and the fundamental. So it's really going to be about 1.8 or something like that. So we should make a parametric sweep in order to sweep over all the broadband to find the dispersion profile. And so look here, if you add a parameter name, you could find sample frequency, and then here's a range where we'll say, I don't know, 165 terahertz, 1 terahertz step, then 215 terahertz. I guess that's basically well covers the telecom band. And, oh yes, and don't forget to, wait, just go back here. We're only going to find one mode, just the TE mode, just the TE mode. I think that should be good. Oh yeah, that's right. And we'll make a probe for the answer that we actually want. We actually want to find the effective refractive index. So let's make a global variable probe. Effective index. And that happens to be this variable. If you don't know what any of the intrinsic variables are named, you can go into equation view, and there's actually over here in the wave equation, there are all these intrinsic variables. So that's how I know. Okay, so we have the probe there, so now we could just run. Look. Probe table. Luckily for me, the probe table is already open. I'm not sure. Sorry? You see this little eye icon where my mouse is? It's in there. So here it's just going through. It's going through every frequency and calculating the refractive index of the fundamental mode. So it's basic as that, really. I better just speed up and just load the finished version for me. Straight waveguide. No. Okay, so you should. I'm I'm not sure if you'll get a graph. You could make a graph. You could find out if you want to make a graph or not, and it should sort of look like that. Basically, of course, you get a higher refractive index for a larger frequency because the mode is more confined. But anyway, if you don't have a table, you find the effective mode index, oh no wait, you find definitions, and you go update probes, and hopefully there should be a table. There should be a table somewhere. If you don't have the table, you could load the example in the tables there. So here's a table. Now what you could do is you could copy that into any kind of numerical organizer of your choice, Excel or Mathematical or MATLAB. I'm going to use MATLAB. But basically the idea is, and I'll return to the slideshow. The idea is basically the propagation constant is linked to the frequency by that kind of relation, the dispersion relation, and we can find the group velocity coefficient. Yeah. All right. You can find the group velocity coefficient by just taking the derivative of that relation, and then the group velocity dispersion coefficient by taking the derivative again. For numerical purposes, you might want the relative phase change relative to the pump frequency. And you could get that by basically having the overall K profile and then subtracting the pump phase and the group velocity phase. And you get sort of graphs like this. On that second one, you can't see the grid, I'm sorry, but it dips below 0. For the telecom band, and that's great because we want anomalous dispersion, because that means we'll get phase matching. In order to do that anyway, you'll find data file in the Google Drive, say in Excel form or MAT form. You'll find it as this name. So if you were to load that data, you might get a data table like this. And also I have a MATLAB script if you're using MATLAB. Let's just go process K, straight waveguide. This is just an example. So basically, I'm just doing just that. I'm getting all the variables I want. I'm fitting a polynomial, and then I'm personally differentiating that polynomial in order to get K1 and K2, and basically doing all that stuff on the slide. And that gives me those sorts of graphs, and that's how I know what I want. So that's dispersion in a waveguide. For dispersion in a resonator, for example, if you have the information you need and you actually want to make a final cavity, maybe it's a ring cavity, so you could just do the exact same thing, except rather than 2D geometry, you do 2D axisymmetric geometry, and simply just move your waveguide by the radius. And when you calculate the modes on Comsol by doing that, you'll find that the mode profile becomes bent. It becomes leaning towards the side of the waveguide. And this may quite dramatically change the dispersion profile, or it might slightly change the dispersion profile, depending on how tightly confined the mode is. I'll show you the example. This is the one that's uploaded. I'm pretty sure it's bent waveguide gigahertz. So here it's exactly the same as the previous model, but here I've got this parameter here, radius. That's 120 microns, and this means that this mode is just slightly bent. And everything else is basically exactly the same. It really is. Except the thing about 2D axisymmetric, when figuring out mode analysis, it does not actually give you the refractive index as an answer. what it gives you is an answer that is of dimension refractive index times radius. So what you would do here is you would search for modes around 2 times radius. And that's why it actually gives you, it would give you these kinds of crazy tiny numbers here for the effective mode index. That's because it's basically the effective mode index times radius. If you solve everything, yes?
What about the number under the physics interface? Do you include the assumption?
No, you leave that blank because you are inputting a frequency to the solver, and then it is telling you the propagation constant. So
please show again where do you input the propagation constant around each of them?
and you put it in the mode analysis step. Search for modes around this. So for the straight waveguide, you just put in 2 because the refractive index is 2. Here I'm going for the effective mode index. But here it's lying to you. It's not really getting the effective mode index. It's getting you the effective mode index times radius. This is just something I found out. But actually, analytically speaking, this is quite convenient because, as it happens, the mode number is essentially this value. Now, and since it gives you NR, basically all you need to do is just convert to mode number like that. And because you're inputting frequency, it does not... so here I actually put in an expression for non-integer mode index by putting exactly that expression in it. And that's given me a table of non-integer mode indexes. So this is... this says basically if you insert a frequency within a cavity, it will be like 741.44 that mode, and that's fine for calculating dispersion because you don't really need to know the exact mode locations. You just need to know how much they deviate. And so you do the similar thing in MATLAB, except you do similar sorts of relations. So with, if you have a function of the mode index and frequency, you can then find the mode spectrum of the cavity by, I guess, saying, you know, d omega by dm, that's the change in frequency per change in mode. That's your FSR. Great, then you know that exactly, and then you derive that again to get your change in FSR per FSR, which is the mode dispersion, the D2. And to get an overall picture of whether modes are matched or not, you could just take the overall mode spectral function and then just take away your pump mode and the FSR function. And that will give you your deviation of modes from the pump frequency. So like over here, it's that relation I showed you in the earlier slide. All the modes are gradually deviating by this many hertz for this frequency, around 192 terahertz. And if you actually do this, you'll find that this is definitely more accurate than the straight waveguide approximation, of course. If your resonator is huge, then it'll really, like a really low curvature, then this way and the straight waveguide way will match up quite closely. If it's a really tightly confined resonator, then you must definitely do the bent waveguide way of doing things, because that will give you a much more accurate, different kind of answer. And yes, I believe that's it. Yeah, so for example, here's an exercise that you could do. You could just do you could make the model from scratch if you like, or use the model I uploaded. Take the script as a guide on maybe how to process the data. You're just doing a differential. You're just deriving the result twice in order to get the dispersion values to find out if you're going to have anomalous or normal dispersion, as in positive or negative dispersion, and what the window of that is in frequency. The exercise example is if you basically just do the same, basically try to do what I've demonstrated in the demonstration, in the presentation that is, and also calculate the TM fundamental mode. And you'll in fact find in the TM fundamental mode, when you plot the mode deviation for that 120 micron radius resonator, you'll find it, well, there should be grid lines there, but you'll find it again crosses 0 for 0 mode deviation at around 150 terahertz. And this means that you will get resonant radiation. So that's a very useful thing to know. So are there any questions about the model? About anything? Or about dispersion? Yes?
How does it work with definition of the dispersion? Because you are inputting it before you actually solve the model. So when you are creating the custom material, you are putting there the variable lambda 0, but you have not solved for it.
Yes. Oh, yes. Great question. Okay. Okay, so in materials, here I've got SIN for the core. Sorry, everything's squished. Variable SIN. And then under variables, this expression for the refractive index is a function of lambda, yeah. But that lambda, that's just C divided by the frequency, C divided by sample frequency. This variable here just calls, the speed of light divided by that.
So it's the frequency around which you are searching. It's not the frequency
Yes.
of the mode.
Yes, it's the frequency that you're searching at.
It's the frequency of the mode, because Comsol handler, he does this iterations, or maybe just some linearization extrapolation.
Oh yeah, okay. In here, wait, okay. Based on that frequency, this goes in here. This gives you the exact. That would give you the exact material refractive index at the frequency that you are sampling, and that's why, and therefore it'll give you the exact propagation constant, or the exact effective refractive index of the propagating mode. The actual mode, when you imagine that it's in the resonator, will not necessarily be integer, but it still will give you a relative mode spectrum, a mode array, for you to calculate an effective dispersion profile. You do not need the exact frequency of every mode. You just need the shape of the mode deviation, basically. To get the exact mode numbers, you just go, like I said, propagation constant times L over 2 pi, and that'll give you what modes correspond to a 2 pi phase shift around the cavity. That's after the fact, basically, in your data processing. But in this way, this will give you the dispersion profile, the profile. Any other questions? Okay. So yeah, yes?
Just if you're looking to do this frequency-dependent effective mode index plot,
Mm-hmm.
you're getting with the
Yep.
probe,
Yep.
but you're finding more than one mode because for some reason there's two very close modes that Comsol finds. Is there another way than having to specifically say, oh, only one mode of this effect?
2 modes. Ah, okay. So what I did when I did my, I basically looked around first to make sure that if I put solve for one mode here, it'll get the mode I want over the bandwidth that I'm searching for. So that's why it's useful to check first. Maybe in an exotic situation you might have modes cross, in which case you'll start finding a different mode. In that situation, it'll be good to, like Hairun was talking about, you can do all of this with MATLAB Live Link. And you could set up many probes, like in his example, where in addition to these probes, you might have a probe that integrates the field and determines whether it's TE or TM, or you might even integrate the field and determine whether it's a fundamental or a second harmonic. And if you are operating this with MATLAB, you could check that, and then if that's not the mode you want, you say, okay, give me the mode after that, please, and then you get that mode instead. That's what we usually do. We do actually every time we search a frequency, we do search for, say, 6 modes, but we check the characteristics of those modes and then order them accordingly in our table, basically. Yeah. But for simple examples, you can kind of jury-rig the system, so it will definitely just give you the mode you want over the bandwidth you want, probably. Any other questions? If not, if you're trying to do anything and you're not sure what's going on, just find me during the exercise section. Okay, thanks.